Hello everybody, this is I'm a guy that you don't know, because I've never made a video before, but I'm here making this video because, frankly, I get extra credit in my class, my chemistry class, if I make this video and put it on YouTube. And, today I'm going to be teaching you all about potential energy graphs, or diagrams. Okay, now these diagrams, I don't have one here, but these diagrams, they show you the energy stored within reactants and products, and the reaction itself. So here, let's just start off with something, just a basic, simple, what's it called, formula, yeah. A plus B, goes over and turns into AB after a reaction. That's the reaction. Now, what a potential energy diagram does is it plots the energy through across everything. So, like across the reaction. So what we do here, we're just gonna mark these here with 0, 10, 20, and 30. No idea. Let's just go up to 40. Going to be wild this time. Okay, now let's just say that this reaction, this right here, will start it at 20, and then here's the reaction, and then here's the end. Okay, now this is this is what a kind of a really not like sloppy drawing of a potential energy diagram. Now, let's see if I can. Yeah, okay. So this is like a potential energy diagram. And now what happens is this over here is A plus B. This is actually the combined potential energy, so the energy that's stored within it up to this line from here is the combined potential energy of A plus B, which is 20. And it's just a good note to throw in here. This is all measured in kilojoules. Okay, so this is 20 kilojoules right here is A plus B. Now same goes for over here. This is potential energy of, you guessed it, the products. A plus B, and it's not AB. It's like, this is just a synthesis reaction. Synthesis. So synthesis reaction. Now, what happens? So it's just a synthesis reaction. It's just where you have one thing and it combines with another thing. So two things form into one thing. Just for those of you that didn't know. Now, back to this. This is an exothermic reaction because it started out. Because here's the potential energy of A plus B is 20 kilojoules, and the potential energy of the products right here, these are reactants, products. Potential energy of the products is 10 kilojoules. Now, if you subtract this, the change is, it's 10 kilojoules. I mean, is that right? No, it's not. The change is 10. You start with the products. Okay, 10 kilojoules subtracted from 20. This makes negative 10. Negative 10 kilojoules is the change in energy. I don't know energy, I'm just an E. The change in energy is 10 kilojoules because over the course of this reaction, it is losing energy. Okay? So that's what makes it exothermic. I'll write it down here just if you can read my handwriting. So exothermic. Now, an exothermic reaction is where the reactants and the products have less potential energy than the reactants. So the combined potential energy of this is 20 kilojoules, and the potential energy of this is 10. So it loses 10 kilojoules from here to here. Okay? So that makes it exothermic. Now, a lot of times, exothermic reactions, like if you actually have the chemicals with you, the thing will get hotter much to your surprise, because it is losing energy. And oh yeah, and when it loses energy, it gets hotter, because because it's making everything hotter around it. So like if you have it in a beaker, it'll make the glass hotter because it's releasing energy onto that beaker. But if it is endothermic, then it will absorb energy, and it will get colder because it is absorbing all the surrounding energy. But it's very important actually to note that this is, as this may seem at first, this is not heat. So it would look like it's getting colder, making it seem endothermic, but it's in fact losing energy, because oh no, this side is not heat. No, this is energy. So it's losing energy, not heat. They're different. And this bottom line, this is the time that passes. I probably should have said it at the beginning. But so energy, time. Energy, time. Energy, time. You got it? Good. Okay. Now this right here, this is the interesting part. This is the reaction itself, is this little hump on the diagram. Now, what this little hump is the energy that actually happens in the reaction, the energy that the reaction uses. So right here, if I start here to this little dotted line, if I make it go up, this entire shaded area is that's the activation energy. Not the entire shaded area, just from this point to this point is the activation energy, which is the minimum amount of energy required to start the reaction. Now, if you'll notice, this is the whole activation complex from here to here. I think so. I'm not sure. I want to Google that, but that's from here to here, I believe, is the activation complex, because what happens is, to make the reaction happen, there needs to be 40 kilojoules that exist. But these reactants already have 20, you see? So when they get 20 more, because the activation energy is 40, when they get 20 more kilojoules, there's already the 20 that they hold, that they absorbed before. I don't know when, I don't know where. All I know is that they have 20 kilojoules. They absorbed it before, so they absorb, wait, what am I saying? Oh, yeah. They absorbed it, they need 20 more, make 40, then the reaction happens. The reaction happens, and there's 40 total kilojoules. You get it? 40 total. But now, see, there's a problem here, because this is an exothermic reaction. So there's 10. By the way, this is the activation energy, if I didn't say it before, but this is 10 kilojoules for the products. So if you wanted to do the reverse reaction, which is if it went backwards, let's say this is in equilibrium, okay? If it's going backwards, it actually takes more energy because it's exothermic, because see, this is 10 kilojoules for its potential energy. So now it would need 30 in total. It would need 30 to get to 40 in total to start the activation energy and to break this apart into A plus B. Okay? If you don't, now that's pretty much it. It's not a very complicated thing, but it's important. So and by the way, this is what an endothermic graph is. It has more energy afterwards. Endothermic. I'll draw a line to endothermic. Well, anyway, that's pretty much it. If you have any questions, or if you've watched this and saw that I made a mistake, or even left something out, please say so in the comments. Now, have a good day, everybody, and enjoy your science, I guess. I don't know. Yeah, enjoy it.